For generations, we gazed at the cosmos, convinced it was vast, yet ultimately decipherable. A universe roughly 14 billion light-years deep, holding a few hundred billion galaxies. An immense picture, yes, but one we felt we understood. Then, the James Webb Space Telescope turned its golden eye towards what appeared to be utterly empty space, and that comforting certainty vanished. Webb revealed an observable universe nearly 93 billion light-years across, brimming with stars and fully formed galaxies where none were expected. It found cosmic structures too grand for their age, black holes defying growth limits, and galaxies already mature just 300 million years after the Big Bang. The most unnerving revelation isn't just the sheer distance Webb can see. It's what these discoveries imply about what lies beyond our cosmic horizon, and why much of the universe may be forever out of reach. To truly grasp Webb's impact, we must abandon a simple idea, that space is merely something we look across. In the universe, distance and time are inseparable. Light, the universe's ultimate speed limit at 186,000 miles per second, still takes time. And time, on cosmic scales, means delay. The farther light travels, the older the image it brings. Our night sky isn't a live broadcast. It's an archive. Every photon is a messenger from a different moment in cosmic history. The more distant its source, the older the message. But this cosmic archive isn't perfectly preserved. As the universe expands, space itself stretches. This stretching distorts light, elongating its wavelengths. Energetic blue and ultraviolet light from ancient sources shifts towards red, eventually slipping into the infrared. This redshift isn't just a visual trick, it's a precise record of cosmic expansion since that light began its journey, a cosmic clock. For decades, telescopes like Hubble, optimized for visible light, showed us nearby wonders. But the light from the most ancient galaxies, stretched by billions of years of expansion, had faded beyond their visible range. It hadn't vanished, it had simply shifted. The James Webb Space Telescope was built to chase that missing light. Its 21-foot gold-coated mirror, operating nearly 1,000,000 miles from Earth in extreme cold, is designed to capture these faint infrared whispers. A warm telescope would drown out such signals, so Webb had to become quiet enough to hear the universe's earliest stories. When Webb stares into a patch of sky that looks completely black to our eyes, it isn't searching for emptiness. It's waiting. Waiting for photons stretched almost to invisibility, arriving slowly, sometimes one by one. Hours, even days, spent collecting light that has journeyed across nearly the entire observable universe. And what it finds is no quiet, tentative beginning. It finds a universe already vibrant, already busy. Some galaxies detected by Webb formed when the universe was only 300 million years old, less than 3% of its current age. Imagine the entire history of the universe compressed into a single year. These galaxies ignite on January 2nd. Traditional models, describing this cosmic dawn, predicted a dim, fragile era. The first stars were expected to ignite slowly, galaxies would be small, delicate collections, taking hundreds of millions of years to mature. Instead, Webb saw galaxies already bright, massive, and furiously forming stars. Some were luminous enough that even if they were far more distant, Webb could still easily detect them. This brightness matters. It demands vast populations of stars. Stars, in their cores, forge heavier elements like carbon and oxygen, elements absent in the primordial universe. These elements are released only when stars die. When Webb finds heavy elements in such incredibly young galaxies, it's undeniable evidence. Earlier generations of stars must have already formed, lived, and ended their lives. All within the universe's first few 100 million years. The cosmic clock, it seems, was pushed backward. The universe didn't slowly ease into complexity, it accelerated towards it with a startling, unexpected speed. This profound mismatch, the too much light too early problem, deeply troubled astronomers. Theory predicted early galaxies would produce little total light. Webb's observations exceeded those predictions by factors of 2, 5, even 10. This wasn't a rounding error, it was a fundamental challenge. Scientists rechecked everything. Measurements, instruments, data. The result held: the early universe was not dim, it was profoundly luminous. Some early galaxies were so massive they were called universe breakers, their existence seemed to defy the very limits of standard cosmology. Galaxies of that size, at those ages, should simply not exist. Even accounting for intensely active supermassive black holes inflating apparent brightness, the early universe still contained roughly twice as many massive galaxies as theory allowed. The tension lessened, but the problem remained. And at the heart of many of these early galaxies, another mystery looms: supermassive black holes, weighing millions or even billions of times our Sun's mass, already in place when the universe was less than 500 million years old. Conventional physics states this shouldn't be possible. Building a black hole of that scale, even under ideal conditions, should take far longer than the early universe permitted. Yet, Webb keeps finding them. This forces astronomers to consider possibilities once deemed extreme: direct collapse of gas clouds, supermassive first stars, or far more frequent black hole mergers. None are confirmed, none are ruled out. These early galaxies and black holes were the architects of everything that followed. Their radiation transformed the universe, their supernovae seeded it with elements, their gravity drew matter into the first large-scale structures. If they formed so early, so efficiently, then the entire timeline of cosmic evolution shifts. As Webb continues to peer deeper, the pattern is undeniable. The universe didn't patiently become complex. It rushed. It assembled stars, galaxies, and black holes at a pace that fundamentally challenges our best equations. A realization that becomes impossible to escape when Webb does something even more unsettling: it begins to count how many galaxies actually exist. For most of the 20th century, astronomers believed they had found a reasonable answer to one of the biggest questions imaginable: how many galaxies exist in the universe? The method was simple in principle. Point a powerful telescope at a tiny, seemingly empty patch of sky, count every detectable galaxy, then scale that number up. When the Hubble Space Telescope performed its deepest observations, it revealed nearly 10,000 galaxies in a region no larger than a grain of sand held at arm's length. That image was shocking. From it, astronomers estimated the universe contained a few hundred billion galaxies. An almost incomprehensible number, which stood for years. Then, the James Webb Space Telescope looked at the same darkness. Where Hubble saw black gaps between galaxies, Webb detected faint infrared glows. Where Hubble observed smudges barely rising above the noise, Webb resolved intricate structure. Regions that once felt empty suddenly revealed themselves as crowded, layered, and alive with distant systems previously invisible. This wasn't a failure of Hubble. It was a limitation of wavelength. As the universe expands, light from distant galaxies stretches into the infrared. By the time it reaches us, it no longer resides in the visible range Hubble was designed to study. The galaxies were always there, their light had simply slipped past our eyes. Webb was built to catch it. In one of its most ambitious observations, Webb surveyed a region of sky slightly larger than 3 full moons placed side by side. For hundreds of hours, it collected over 10,000 individual exposures, each capturing faint infrared signals that had traveled across cosmic time. When combined, the result was staggering. Nearly 800,000 distinct galaxies filled the frame. 800,000 galaxies in a patch of sky most would dismiss as utterly empty. To grasp this scale, imagine printing the famous Hubble ultra-deep field on a standard sheet of paper. To show Webb's image with the same detail, the print would need to be more than 13 feet tall and 13 feet wide, a wall-sized mural of cosmic history. And every single point of light in that mural is not a star. It is a galaxy. Each of those galaxies contains millions, billions, or even trillions of stars. Many host planetary systems, many harbor complex chemistry, dust, and heavy elements forged by generations of stars. The universe, it turns out, is not sparsely populated with isolated islands of matter drifting through darkness. It is densely packed, layered with structure at every imaginable scale. What makes this discovery even more powerful is that Webb didn't just count galaxies. It measured them. For each one, astronomers can estimate its distance, its mass, its rate of star formation, and its approximate age. This allows scientists to reconstruct how galaxies changed over nearly the entire history of the universe, tracking growth from the early cosmic dawn to the present day. And when they did that, a deeper pattern emerged. Galaxies are not scattered randomly through space. They cluster. They align. They trace invisible pathways. On the largest scales, the universe resembles a vast cosmic web, long filaments of matter stretching tens and hundreds of millions of light-years, intersecting at dense nodes where galaxy clusters form, separated by enormous voids where almost nothing exists. This structure had been predicted for decades, but Webb revealed it with unprecedented clarity. Many of the galaxies Webb detected were hidden behind dust that blocks visible light but allows infrared wavelengths to pass through. Entire populations of dusty, star-forming galaxies suddenly appeared, filling in gaps where earlier surveys saw emptiness. The cosmic web didn't just become clearer, it became far more crowded. This matters because the distribution of galaxies isn't random decoration. It's a record of how the universe grew. Shortly after the Big Bang, matter was spread almost evenly throughout space, with tiny fluctuations in density imprinted during its earliest moments. Regions that were slightly denser exerted slightly stronger gravity. Over time, matter flowed toward those regions, amplifying the differences. Gravity carved space into filaments and nodes, draining matter from surrounding regions and leaving behind vast voids. The universe evolved much like rainfall over uneven terrain. Water drains into valleys, carving rivers and channels while higher ground is left dry. Over time, a structured landscape emerges. Webb's observations show this process was already well underway, surprisingly early in cosmic history. Filaments tens of millions of light-years long existed when the universe was only a few billion years old. Some structures were so large and so organized that they challenged expectations about how quickly matter could arrange itself. If Webb's deep fields are representative, and multiple observations in different directions suggest they are, then the total number of galaxies in the observable universe may not be hundreds of billions, but trillions. For every galaxy we once thought existed, there may be 10 more hiding beyond what earlier telescopes could detect. That revision changes everything. More galaxies mean more stars. More stars mean more planets. More planets mean more opportunities for complexity to arise. The universe becomes not just larger in size, but richer in possibility. Yet even this staggering abundance exists only within the observable universe. Beyond that boundary, space continues, galaxies continue, structure continues. James Webb has shown us that even the portion of the universe we can see is vastly larger and more crowded than we believed. And that realization forces an even deeper question. If reality is this rich within our visible horizon, what does that say about the true scale of everything that exists beyond our view? At first glance, the universe seems easy to measure. The Big Bang happened about 13.8 billion years ago. Light travels at a fixed speed. So it feels natural to assume that the farthest objects we can see should be about 13.8 billion light-years away. For a long time, even scientists spoke about the universe as if that were true. But that intuition quietly breaks down the moment we take cosmic expansion seriously. The observable universe does not have a radius of 13.8 billion light-years. It has a radius of about 46.5 billion light-years, making its full diameter roughly 93 billion light-years. This is not speculation or artistic license. It is a measured result supported by observations of cosmic expansion and the behavior of ancient light. The reason this number feels impossible is because it clashes with how we instinctively think about motion. Nothing can travel faster than light through space. And that rule still holds. No galaxy is racing through space at impossible speeds. No signal is breaking the cosmic speed limit. Instead, the universe has found a way to grow far larger without violating any laws of physics. It does this by stretching space itself. When we say distant galaxies are moving away from us, it is tempting to picture them flying outward like fragments from an explosion. That image is deeply misleading. On large scales, galaxies are not really moving through space at all. They are being carried apart as the space between them expands. A familiar analogy helps make this intuitive. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot. None of the dots are at the center. None of them are moving across the surface under their own power. The surface itself is stretching, and the dots simply go along for the ride. The universe behaves in much the same way. When a distant galaxy emitted the light we detect today, it was far closer to us than it is now. Over billions of years, while that light was traveling toward Earth, the space between us and the galaxy expanded continuously. By the time the light finally arrived, the galaxy that emitted it had been carried tens of billions of light-years farther away. This is why we can observe galaxies whose light has been traveling for 13.5 billion years, even though their current distance is more than 46 billion light-years. Light is not simply crossing a fixed distance. It is moving through a distance that is growing while it travels. In effect, light has been running on a cosmic treadmill. This creates a boundary known as the cosmic horizon. The cosmic horizon is not a wall or an edge in space. There is no place where the universe suddenly stops. Instead, it is the limit of what can ever be observed from our location. Given the finite age of the universe and the way space expands, beyond that horizon, light simply cannot reach us. Not because it lacks time, but because the space it must cross grows faster than light can traverse it. And this is where the universe becomes deeply unsettling. Space does not end at the cosmic horizon. We know this because the universe looks essentially the same in every direction we observe. The distribution of galaxies does not thin out toward an edge. The cosmic microwave background, the faint afterglow of the Big Bang, appears almost perfectly uniform across the entire sky. That smoothness would be impossible if space abruptly ended just beyond our view. So the universe extends beyond what we can see. But it does so in a way that permanently hides much of itself. Beyond 46.5 billion light-years, galaxies still exist. Stars still ignite and die. Black holes still merge. Entire cosmic histories unfold in regions that will never influence us and can never be influenced by us. No signal from those regions will ever reach Earth. Not because our technology is inadequate, but because the structure of spacetime itself prevents it. Even more unsettling, this boundary is not fixed. As time passes, the observable universe grows larger because light from more distant regions has had more time to reach us. The horizon creeps outward. But at the same time, cosmic expansion is accelerating, driven by dark energy. Space itself is stretching faster now than it did in the past. These two effects compete with one another. The result is a universe where some objects briefly become observable, only to later slip beyond reach forever. Galaxies we can see today are not guaranteed to remain visible indefinitely. Their light will continue to stretch, shifting into longer and longer wavelengths. Eventually, that light becomes so diluted and redshifted that no telescope could ever detect it. From our perspective, those galaxies will appear frozen at a particular moment in their history, slowly fading until they vanish completely. This is not a theoretical curiosity. It is a direct consequence of measured expansion rates. If the universe continues behaving as it does now, then in roughly 100 to 150 billion years, every galaxy outside our local gravitationally bound group will cross the cosmic horizon. Future observers would see a universe containing only a small cluster of nearby galaxies surrounded by darkness. The evidence of cosmic expansion, the cosmic microwave background, and the vast web of distant galaxies would be gone. They might never know that anything else ever existed. This leads to a profound shift in perspective. The observable universe is not the universe. It is simply the portion of the universe that happens to be observable from where we stand at this moment in cosmic time. Move to another galaxy, and the observable universe changes. Different galaxies enter view, others disappear beyond the horizon. Every location in space defines its own observable bubble. There is no privileged vantage point, no center, no location from which the entire universe can be seen. Every observer, no matter where they are, sits at the center of their own observable bubble. This is why the James Webb Space Telescope is so transformative. By pushing observations closer to the cosmic horizon than ever before, Webb forces us to confront the limits of what observation can achieve. When Webb detects galaxies at extreme redshifts, it is not just showing us ancient objects. It is showing us the boundary of causal connection. Those galaxies are no longer where their light began. Their current state, their later mergers, transformations, and possible destruction, is unknowable to us. That information is still traveling through space, stretched and diluted by expansion, and in many cases will never arrive. What we see is not what is, it is what was. And even that view is incomplete. Beyond the observable horizon lies the unobservable universe, regions that may contain galaxies, clusters, and structures just as rich and complex as those we see. Some models suggest the universe may be infinite. Others propose it is finite, but unimaginably large. Either way, the observable universe is almost certainly only a small fraction of the whole. James Webb has not revealed the edge of the universe. It has revealed that there is no accessible edge at all. And as this realization settles in, another question becomes unavoidable. If most of the universe is hidden by expansion, if vast regions of reality are permanently beyond reach, then something must be driving that expansion to accelerate. To understand that force, we have to confront the most dominant and most mysterious ingredient of the cosmos itself. For most of the 20th century, the story of cosmic expansion seemed straightforward. The universe began in the Big Bang, everything rushed outward, and gravity, the only force considered significant on vast scales, would gradually work to slow that expansion down. Astronomers debated whether the universe would expand forever or eventually collapse back in on itself, but the underlying assumption was always the same: gravity was in control. That assumption did not survive contact with observation. In the late 1990s, astronomers studying distant stellar explosions noticed something deeply unsettling. These explosions, known as Type Ia supernovae, shine with a remarkably consistent brightness. Because of that reliability, they act like cosmic mile markers. By comparing how bright a supernova appears to how bright it should be, scientists can calculate its distance. Combine that distance with how fast the host galaxy is receding, and the expansion history of the universe reveals itself. What those measurements showed was the opposite of what anyone expected. The universe was not slowing down. It was speeding up. Distant galaxies were farther away than they should have been if expansion were gradually easing under gravity's pull. Something was pushing space apart, not just preserving the expansion, but accelerating it. The farther back astronomers looked, the clearer the pattern became. Expansion had been gaining speed for billions of years. To account for this utterly bizarre behavior, cosmology was forced to introduce a new ingredient: dark energy. Dark energy is not something we can see, touch, or directly detect. It does not emit light. It does not absorb radiation. It does not clump into stars, galaxies, or clouds. Its existence is inferred entirely from its effect on the universe's expansion. And that effect is overwhelming. Measurements now indicate that dark energy makes up roughly 68% of everything that exists. Ordinary matter, everything from galaxies and stars to planets and people, accounts for less than 5%. Dark matter makes up most of the rest. The universe we can see, the universe that feels solid and familiar, is a minor component of reality. What makes dark energy especially unsettling is how it behaves as the universe grows. Normal matter becomes diluted as space expands. Double the volume of space, and the density of matter drops by half. Radiation thins out even faster. Dark energy does not follow these rules. Its density appears to remain constant even as the universe expands. As space grows larger, the total amount of dark energy increases. This creates a runaway effect. More space means more dark energy. More dark energy drives faster expansion. Faster expansion creates more space. Over billions of years, this feedback loop has shifted the balance of power in the universe. Early on, matter dominated. Gravity sculpted galaxies, stars, and the cosmic web. But as the universe expanded and matter spread thinner, dark energy quietly took over. About 5 billion years ago, it became the dominant influence on cosmic expansion. The James Webb Space Telescope does not detect dark energy directly, but it sees its fingerprints everywhere. The extreme stretching of ancient light, the immense size of the observable universe, and the way distant galaxies recede all reflect the influence of this invisible force. Without dark energy, the universe would be far smaller. The cosmic horizon would sit much closer. Vast regions we can see today would never have been observable at all. Dark energy does more than shape the present. It determines the universe's future. If dark energy remains constant, as current observations suggest, then expansion will continue forever, accelerating as time passes. Galaxy clusters will remain gravitationally bound, but everything outside them will gradually slip beyond the cosmic horizon. Trillions of years from now, observers inside a galaxy like the Milky Way would see a lonely cosmos, filled with stars nearby, but utterly empty beyond. The universe would still exist, but it would look almost vacant. Yet, this picture is complicated by one of the most serious unresolved problems in modern cosmology. A problem that James Webb has not erased, but instead made harder to ignore. When scientists measure how fast the universe is expanding today, they do not get one answer. They get two. One method looks deep into the past by studying the cosmic microwave background, the faint afterglow released when the universe was only about 380,000 years old. From the subtle patterns in that radiation, scientists infer an expansion rate of about 67 km per second per megaparsec. The second method looks nearby. Astronomers measure distances to galaxies using Cepheid variable stars and type Ia supernovae, then compare those distances to how fast the galaxies are receding. This approach consistently produces a higher value, around 73 km per second per megaparsec. Both measurements are precise. Both have been repeated many times. Both have been scrutinized for errors. They do not agree. This discrepancy is known as the Hubble tension, and it represents one of the deepest cracks in our understanding of the universe. James Webb was expected to clarify the situation by providing cleaner, more accurate distance measurements. Instead, Webb confirmed the higher expansion rate measured in the nearby universe. The tension did not disappear. It sharpened. This leaves cosmology in an uncomfortable position. Either something is wrong with our measurements, something is wrong with our assumptions, or something fundamental is missing from our models of reality. One possibility is that dark energy is not constant after all. Its strength may have changed over cosmic time, altering the expansion rate in ways our current models do not capture. Another possibility is that unknown physics affects how light travels across enormous distances, subtly biasing measurements. Or the early universe itself may have behaved differently than we assume, imprinting expansion behavior that evolves in unexpected ways. Each possibility carries profound consequences. The expansion rate determines the universe's age, its size, and its ultimate fate. If we are misunderstanding it, then many conclusions drawn from decades of cosmological research may need revision. The problem is not cosmetic. It cuts to the very foundation of how we describe reality. There is also a more extreme scenario that cannot yet be ruled out. If dark energy grows stronger over time instead of remaining constant, expansion could eventually overwhelm gravity even on smaller scales. Galaxy clusters would be pulled apart. Galaxies themselves would dissolve. Star systems, planets, molecules, and eventually atoms could be torn apart in a hypothetical future known as the Big Rip. Current data does not favor this outcome, but uncertainties remain. Measuring dark energy precisely is extraordinarily difficult, and small changes in its behavior could have enormous long-term consequences. What is already clear is that dark energy dominates the cosmos. It stretches space, hides vast regions of reality beyond our reach, and determines what future observers will be able to see. It is the reason the observable universe spans 93 billion light-years. It is the reason most of existence will forever remain invisible. And yet, dark energy alone does not explain the universe we observe. Because while it pulls space apart on the largest scales, something else must pull matter together on smaller ones. Something must counter expansion locally, allowing galaxies to form, clusters to grow, and structure to emerge instead of dissolving into uniform fog. That force is equally invisible, equally mysterious, and absolutely essential to understand how the universe holds itself together even as it expands. We have to turn to the unseen framework that shapes every galaxy, every cluster, and every filament of the cosmic web. If dark energy governs how the universe expands, then dark matter governs how it holds itself together. Without it, the universe revealed by the James Webb Space Telescope would not exist in any recognizable form. Galaxies would never have assembled. Clusters would have flown apart. And the vast filamentary structure stretching across the cosmos would have remained a nearly uniform fog of matter. Dark matter does not shine. It does not absorb light. It does not emit radiation of any kind we can directly detect. And yet, it outweighs everything we can see by more than 5 to 1. Roughly 85% of all matter in the universe is dark matter, detectable only through its gravitational influence. Every star, planet, nebula, and galaxy is built within a framework dominated by something fundamentally invisible. The first clues to its existence emerged nearly a century ago when astronomers noticed that galaxies were behaving in ways that made no sense. Stars in the outer regions of spiral galaxies were orbiting far too fast. According to the gravity generated by visible matter alone, those stars should have been flung into intergalactic space. Instead, they remained bound, moving as if each galaxy were embedded in a massive, unseen halo. That unseen mass was dark matter. As observations expanded, the evidence became impossible to ignore. Entire galaxy clusters showed the same problem on much larger scales. Individual galaxies within clusters moved too quickly to be held together by stars and gas alone. Gravitational lensing revealed distortions in background galaxies far stronger than visible matter could produce. Again and again, the conclusion was unavoidable: most of the universe's matter is invisible. What makes dark matter so important is not just how much of it exists, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself or lose energy by emitting radiation. It passes through space almost frictionlessly. This allowed it to begin clumping extraordinarily early in cosmic history. Shortly after the Big Bang, the universe was nearly uniform with tiny density fluctuations imprinted during its earliest moments. Dark matter responded to those fluctuations first. While ordinary matter remained hot and resisted collapse, dark matter quietly gathered into growing concentrations, forming massive invisible halos long before the first stars ignited. These halos became the scaffolding of the universe. As the universe cooled, ordinary matter began falling into these dark matter wells. Gas collected, compressed, and eventually ignited nuclear fusion. Stars formed, galaxies assembled. Not randomly, but precisely where dark matter had already gathered. The visible universe traces an invisible blueprint laid down billions of years earlier. This process produced one of the most striking features of reality, the cosmic web. On the largest scales, matter is arranged in vast filaments stretching tens to hundreds of millions of light-years across. These filaments intersect at dense nodes where galaxy clusters form. Between them lie enormous voids, regions so empty they contain almost no galaxies at all. This structure is not artistic coincidence. It is the natural outcome of gravity acting on dark matter over cosmic time. James Webb's observations have brought this architecture into sharper focus than ever before. By cataloging hundreds of thousands of galaxies and measuring their distances, astronomers can map the three-dimensional distribution of matter across the universe. The pattern is unmistakable. Galaxies line up along filaments. They cluster at intersections. They are void in vast empty regions. The visible universe follows an invisible skeleton. What makes Webb especially powerful is its ability to see through dust and detect faint distant galaxies that previous surveys missed. This fills in gaps in the cosmic web, revealing how early these structures emerged. Webb has shown that filaments were already well established when the universe was only a few billion years old, and that matter was flowing along them into growing clusters. This flow is not just a metaphor. Simulations and observations indicate that gas streams along dark matter filaments like traffic along cosmic highways. Galaxies grow not only by forming stars internally, but by continuously accreting fresh material delivered along these invisible routes. Even our own galaxy participates in this process. The Milky Way resides on a filament connecting larger structures, drifting through space along pathways defined by dark matter. On these scales, motion is guided, not random. For decades, the role of dark matter in shaping the cosmic web rested largely on simulations and indirect evidence. But recently, astronomers achieved something remarkable. They detected dark matter directly along the filaments themselves. Using gravitational lensing, scientists measured how light from distant background galaxies was subtly distorted as it passed through regions where filaments were predicted to exist. The distortions were faint and difficult to detect, but consistent. They revealed mass where no visible matter could account for it. Dark matter was not just concentrated in clusters. It was stretched across space, threading the universe together. This transformed the cosmic web from a theoretical construct into an observed structure. The universe is not a loose collection of galaxies drifting apart. It is an interconnected network shaped and sustained by invisible matter. The nodes of this network are galaxy clusters, the most massive gravitationally bound objects in existence. A single cluster can contain hundreds or thousands of galaxies, along with vast reservoirs of superheated gas and enormous quantities of dark matter. These clusters act as anchors, pulling matter along filaments toward their centers. When galaxies fall into clusters, they experience dramatic changes. The dense environment strips away gas, shuts down star formation, and reshapes galactic structure. James Webb has captured these transformations in detail, showing galaxies mid-transition as they are altered by their surroundings. The cosmic web is not static. It is active, dynamic, and constantly reshaping the universe. Yet, for all its influence, dark matter remains one of the greatest mysteries in physics. We still do not know what it is made of. It may consist of unknown particles beyond the standard model. It may involve entirely new physics. Despite decades of experiments, dark matter has never been directly detected in a laboratory. And still its presence is undeniable. Every galaxy rotation curve, every lensing map, every large-scale structure survey points to the same conclusion. Remove dark matter from the equations and the universe we observe simply cannot exist. James Webb does not solve the dark matter mystery, but it strengthens the case for its central role. By revealing how quickly structure formed in the early universe, Webb shows that visible matter alone could never have done the job. Dark matter provided the gravitational head start needed to assemble galaxies just a few 100 million years after the Big Bang. It also explains why the universe looks the way it does today. The vast emptiness of cosmic voids, the dense richness of clusters, and the filamentary bridges connecting them all emerge naturally when dark matter dominates gravity. Yet even this invisible framework operates within a universe being pulled apart by dark energy. Dark matter builds structure. Dark energy stretches space. The universe exists in a constant tension between these two unseen forces. On smaller scales, gravity wins. Galaxies form. Clusters grow. On the larger scales, dark energy prevails, driving galaxies apart and pushing regions of space beyond our cosmic horizon. James Webb has shown us that the universe is not merely larger than expected. It is more organized, more interconnected, and more dependent on invisible forces than we ever imagined. What we see, stars, galaxies, nebulae, is only the illuminated surface of a far deeper structure, an unseen architecture holding reality together. And when we step back far enough to consider that structure as a whole, another realization becomes unavoidable. Even this vast interconnected universe is only what we can observe from our position in space and time. Beyond it, the universe continues, shaped by the same invisible forces, unfolding beyond any horizon we can ever cross. So, the universe is not just bigger, it is filled with unseen forces, with mysteries that deepen with every new discovery. Imagine, for a moment, that the total number of galaxies in the entire universe, not just the observable part, could reach a staggering 100 trillion.